Hello students, welcome back to the classroom point. In our previous class, we have discussed about the electrode potentials, cell potential and their definitions and how to calculate the EMF of the cell. So in today's class, we shall discuss the standard hydrogen electrode and its functioning and how to use the standard hydrogen electrode in finding the single electrode potentials of the other electrodes. So let us see here. Standard hydrogen electrode is also known as the normal hydrogen electrode, usually mentioned as either SHE or NHE. So basically, standard hydrogen electrode is a reference electrode. Usually, single electrode potentials of any electrode cannot be calculated independently. So that we need some reference electrode to calculate the single electrode potential of the other electrodes. So in this reference electrode, the EMF of this standard hydrogen electrode, E0 value of this standard hydrogen electrode is taken as 0.00 volts. So arbitrarily taken as 0.00 volts. That means we also don't know exact value of this one, but it's a fixed one. So that based on this, we can calculate the other electrode potentials. So whatever the cell value is there, that is their electrode potentials. We shall see all those. So let us see here the description of the standard hydrogen electrode. Standard hydrogen electrode contains a beaker in which 1 molar hydrochloric acid is taken and a glass tube is dipped into the 1 molar of the hydrogen chloride solution. This glass tube contains a platinum foil which is half projected towards the hydrochloric acid and half is in the glass tube. So this hydrogen electrode finally connected to the one metallic wire which is we use to connect to the other electrodes. And this particular glass tube is filled with the hydrogen gas at 1 bar of the pressure. This standard hydrogen electrode can act as both anode and cathode. So we can use it as both cathode as well as the anode. Let us see how this is working when it is acting as anode and how it works when it acting as the cathode. So let us see here anode. When it functions as anode, oxidation reaction takes place. Oxidation reaction means here, in hydrochloric acid, H plus and Cl minus ions are present. Only H2 gas can oxidize to H plus ions. So oxidation means here, hydrogen gas, whenever you fill into this glass tube, so it is absorbed over the surface of this platinum foil and there it gets oxidized and releases the electrons. So that here the reaction takes place. Hydrogen gas oxidized to H plus ions in aqueous form plus electron. So in this process, hydrogen gas is converting into the H plus ions. So then how to represent the standard hydrogen electrode when it is functioning as the anode? Basically, this hydrogen gas is absorbed over the surface of the platinum foil. So that initially platinum we have to write down. Why? Because the oxidation reaction is taken place on the surface of the platinum. This platinum metal is in the solid state. And a solid state, gaseous state, different phases are there. When phase is changed, we have to put one vertical line. Next, hydrogen gas. In gaseous state, its pressure is 1 bar. Next, hydrogen gas is changed to the H plus ion. In aqueous state, H plus ion concentration is 1 molar. So this is the representation of the standard hydrogen electrode when it is acting as anode where oxidation reaction is taken place. Now let us see if it functions as cathode, then how the reaction takes place and how the cell is to be represented. Here, when it is function as the cathode, automatically reduction reaction takes place at the cathode. Reduction of H plus ions takes place. So that here H plus ions goes to the platinum foil and they get the electrons when it is connected to the other electrodes. It is in aqueous state. Electrons are gained so that half mole of the hydrogen gas is released. This is again at 1 bar. Now this representation is starting. H plus ion is there, so that you write down the H plus ion. In aqueous form, its concentration is 1 molar. Aqueous form to the gaseous form, so that phase change is there. Hydrogen in gaseous state. That hydrogen gas pressure is 1 bar. Again phase change because the hydrogen gas is present or absorbed over the surface of the platinum, so that platinum solid. So in both the reactions, in one area it is acting as an anode, another area it is acting as a cathode. Whether it acts as anode or cathode, basically, so its standard electrode potential to be taken as 0.00 volts. So in these reactions, we can observe that H plus ion either is formed or is consumed. That means we can say that the standard hydrogen electrode is reversible with respect to the H plus ions. One ions we take it here. And the disadvantage of the standard hydrogen electrode is, whenever it is acting as anode, hydrogen gas is completely converted to the H plus ions. So the pressure of the hydrogen gas gradually decreases and concentration of the HCl gradually increases. When it acts as the cathode, H plus ions are reduced, hydrogen gas is released. So the concentration of HCl decreases, pressure of the hydrogen gas increase. So maintaining the pressure of the hydrogen gas at 1 bar and the concentration of HCl at 1 molar is a difficult task while using the standard hydrogen electrode. But it is a better electrode to find out the electrode potentials of the other electrodes. Now let us see how, when this is connected to the other electrodes, and how to write down the cell reactions as well as how to find out the standard electrode potentials. So in this condition is, let us consider SHE as anode. So in all these reactions, I am going to consider standard hydrogen electrode as the anode, and other electrode, whichever I am going to find out, that I am going to take it as a cathode. That means if you observe the galvanic cell, you might have remembered that a small rough diagram I am writing here. One side anode part, the other side cathode part we are taking. Here zinc rod is dissolved in the zinc sulfate, this side copper rod is dissolved in the copper sulfate, salt bridge is present, these are connected. So in the place of this zinc rod in zinc sulfate solution, I am going to place the standard hydrogen electrode. So the standard hydrogen electrode metallic wire is connected to the cathode, whichever electrode I am going to take. We can take any type of electrodes here. So now let us connect this standard hydrogen electrode SHE as anode and copper electrode I am going to take as cathode. Copper electrode as cathode. So we know that when standard hydrogen electrode is taken as anode, automatically oxidation reaction takes place at anode. So we shall write down that reaction at anode. Oxidation reaction means H2, gaseous state, 1 bar pressure, converting into the to H plus ions, aqueous state, plus 2 electrons. This is 1 molar of concentration. What I am going to I am going to take it as a reference part. The question arises, what about earlier we have taken the half mole of the hydrogen gas, now we are taking the complete H2 gas. Basically we write the reactions in terms of the 1 mole of the ions, so that 1 mole of the H plus means here half H2 gas has to be taken. But when you take the copper as cathode, copper is usually need the 2 electrons. That's why to balance the reaction we have taken the complete reaction. So now at cathode copper ion in aqueous form take up those 2 electrons and shall be deposited as copper solid. So if you write down the complete equation, cancellation things happen, 2 electrons. So we can write down that H2 gas reacts with Cu2 plus an aqueous state, giving 2 H plus ions plus copper solid. So to happen this reaction, whenever this standard hydrogen electrode is taken as anode or copper electrode is taken as cathode, the E naught cell value observed was plus 0.34 volts. That means this cell is possible. Then again question arises how the E naught cell value comes here. Let us take the formula. E naught cell is equals to E naught cathode minus E naught anode. Here standard hydrogen electrode is taken as anode. So anode value is 0.00 volts. So whatever the electrode potential of the cell is there, that potential completely is of the electrode potential of the cathode. So E cell value was observed as plus 0.34 volts. That means that value belongs to the reduction potential of the cathode, that is 0.34 volts. Since E naught cell value is positive, this reaction is possible. So what information we can gather from this reaction is H2 is converting Cu2 plus into Cu. In this case, Cu2 plus reduced to Cu. That means hydrogen gas acting as a reducing agent for the cupric ions and converting them into the copper, or else we can write down that Cu2 plus ions acts as oxidizing agent for the hydrogen gas to convert it into the H plus ions. So here the important thing is we can use the hydrogen gas in the purification of the copper salts to get the copper. Why? Because when hydrogen gas is sent through the copper compounds, that Cu2 plus is converted to the copper metal, so that hydrogen gas is acting as a reducing agent. Now the question is, whenever opposite reaction is not possible, when copper is added to the H plus ion, copper cannot reduce the H plus ions into the H2. That means copper cannot replace the H plus ions. Why? Because if the reverse reaction we are expecting means E naught cell value shall be negative. Negative means it is not the spontaneous reaction. So this H plus ions coming from acid. Acid releases H plus ions. Here acid is HCl. H plus and Cl minus ions. Copper, if wants to replace H plus ions, means copper has to react with the acid. But here copper is not replacing H plus ions into the H2. That means copper do not react with the acids. So most of the metals react with the acids. They remove the H plus ion as hydrogen gas. That means metals reacts with the acids to liberate the hydrogen gas is the fundamental thing. But copper is the metal that cannot release the hydrogen gas when it reacts with the acids. But copper reacts with only one acid, but not for the release of the hydrogen gas. That is, copper reacts with the nitric acid. And in this case, hydrogen gas is not released. But still copper reacts with the nitric acid. Reason is, here nitrate ion, NO3 minus ion, can oxidize the copper into Cu2 plus. Other acids cannot oxidize the copper into the Cu2 plus. So this is the information we can gather from the when standard hydrogen electrode is connected to the copper electrode. Now let us take one more electrode, that is zinc electrode as the cathode. So condition 2 is zinc electrode as cathode. So again anode is standard hydrogen electrode, same reaction takes place. Hydrogen gas state converting into the 2 H plus ions plus 2 electrons, and cathode, again let us take the Zn2 plus ion, take up those 2 electrons, gives zinc solid. When zinc electrode is taken as cathode and standard hydrogen electrode is taken as the anode, the cell potential observed was, E naught cell observed was minus 0.76 volts. That means this cell do not work. So hydrogen electrode as the anode, zinc electrode as the cathode is not possible, but reverse if you do it, it is possible. Let us try to write down the complete equation here. Hydrogen gas state, zinc 2 plus ions, aqueous state, 2H plus ion, plus zinc in solid state. Since E0 cell value for this reaction is negative, this reaction is not possible. We have to reverse the reaction where we have to exchange the electrodes. So zinc as anode, copper as the cathode means then you will get the positive E0 cell value. So here again E0 cathode, E0 cell is equals to E0 cathode minus 0.76 minus 0.00, that value equals to minus 0.76 volts. So now let us imagine the opposite reaction so then we can understand this equation. This reaction is not possible. So this clearly says that opposite reaction. Opposite reaction means zinc solid reacts with the H plus ions, giving the Zn2 plus hydrogen gas. That means here zinc reacts with the H plus ion. H plus ion means acid. So zinc reacts with the acids and liberate the hydrogen gas. But hydrogen gas cannot reduce the Zn2 plus ions into zinc. So when you compare both of these reactions, copper do not react with the acids except nitric acid. But zinc react with almost all acids, releases hydrogen gas. Here hydrogen gas is acting as a reducing agent for Cu2 plus. Here hydrogen gas is not acting as a reducing agent for the Zn2 plus. Then when you take only ions, here Cu2 plus is reduced easily to the Cu, but H plus ion cannot reduce easily. So when copper is taken as the cathode, the reduction of Cu2 plus is more easy than the reduction of H plus ion. When zinc is taken as the cathode, the reduction of H plus ion is more easy than the Zn2 plus ions. Now let us see how to represent these cell potentials, cell representations. So we know that first of all we have to write down the oxidation half cell followed by the reduction half cell. First let us write down the when copper is taken as the cathode. Anode oxidation reaction. Platinum solid, hydrogen gas, 1 bar pressure changes to the H plus, aqueous state, 1 molar, double vertical line, Cu2 plus changes to the Cu. Cu2 plus aqueous state changes to the Cu in solid state. That cell is possible. When it comes to this zinc taken as cathode, since this reaction is not possible, we cannot write down the similar reaction for the zinc electrode, but we have to write down the opposite reaction. Why? Because in opposite reaction E0 cell value equals to positive. So then we can write down that zinc acting as anode now, zinc converts into the Zn2 plus, aqueous form, standard concentration 1 molar, double vertical line. Now here reverse reaction. Reverse reaction means you can take that H plus ion is converting into H2. So H plus ion, aqueous state, 1 molar concentration changes to the hydrogen gas, 1 bar of pressure, platinum in solid state. So this is the way to use the standard hydrogen electrode in finding the standard reduction potentials of any other electrodes. Not only this one, we can take any other electrodes, and based on this one, here we got the two electrode standard electrode potentials. One is copper as cathode, second one is zinc as cathode. When copper as cathode, it is 0.34 is there, and zinc as cathode, it is minus 0.76 is there. Higher the reduction potential is for the copper electrode, lower the reduction potential is for the zinc electrode. So whenever higher the reduction potential is there, that electrode always acts as the cathode. That means whenever you want to join the copper electrode and zinc electrode to construct the cell, in such conditions try to keep the higher electrode potential as the cathode and the electrode potential that is having the lower electrode potential electrode is as the anode. So the fundamental thing is higher the reduction potential acts as the cathode and easy to reduce, and lower the reduction potential acts as the anode and easy to oxidize. That means when you take the copper and zinc metals, zinc can easily get oxidized. So zinc easily participates. When you take the copper and zinc metals, it is easy to oxidize Zn2 plus rather than the copper to the Cu2 plus. When you take the ions Cu2 plus and Zn2 plus ions, then it is easy to reduce the copper into Cu2 copper metal, not the zinc into the zinc solid. So reduction is more possible for the electrode that is having the higher standard reduction potential value, and lower the reduction standard reduction potential value means easy to oxidize. And one more thing here, remember that the metal that is having the lower reduction potential is more active metal, and the metal that is having the higher reduction potential is less active metal. That means here we shall take one more small concept. I'll write down these points. Higher the standard reduction potential acts as cathode, easy to get reduced, and a less active metal. Lower the SRP, standard reduction potential, acts as anode, easy to get oxidized, and more active the metal. So here zinc and Cu, if you take the metal that is more active is zinc, then what is the use of the active nature? Remember that more active metals always replaces the ions of the less active metals from their solutions. That means here zinc, when react with the Cu2 plus ion, since it is more active than this one, it can easily transfer its electrons to electron. That is what here we have written, easy to get oxidized. More active metal easily lose the electrons. The active nature of the metal is because of loss of the electrons, the tendency to lose the electrons. More easily the metal is losing the electrons, we can call the metal is a more active metal. So that here the metal is easily losing the electrons than the copper. That's why this metal loses electrons, and these electrons are accepted by the less active metal. So less active metal gets reduced and more active metal gets oxidized. That's the reason why when zinc rod is placed in the copper sulfate solution, copper sulfate aqueous solution color is blue color. But after some time we can say that it converts into the ZnSO4 plus copper. Means Cu2 plus ion present in the copper sulfate, this ion is replaced by the zinc as the Zn2 plus and copper is completely deposited. That is the reason why we should not keep the salt solutions or the solutions of the less active metals in the pots of the more active metal. That means copper sulfate solution cannot be placed in the zinc pot. Reason is zinc is more active than the copper. That's the reason why zinc slowly replaces the copper from the cupric ions from the copper sulfate solution and occupies its position. Finally, zinc sulfate will be there, copper completely deposits. But opposite we can do that. That means the solution of the more active metal can be placed in the less active metal pots. That means zinc sulfate solution we can carry using the copper pots. So this is the application of the standard hydrogen electrode along with its calculation. So dear students, I hope you understand. We shall meet in the next class. Thank you.